So welcome to video 4 in ST2 on hypothesis testing. So this time we're going to talk about power, effect sizes, and this important issue of looking at things from a biological context and thinking about biological significance if we're going to use the S word at all, but not about statistical significance because it may not have any biological meaning. We don't want to fall into some sort of spell of having small p-values. So we can think about our null distribution like this. We may have a distribution of values. I may have some alpha value threshold, which we use to determine samples that may be more worthy of more testing. Of course, this alpha threshold is arbitrary. We need to be able to think about how moving that left and right can affect what we get. If we think about the comparison of our null hypothesis to our alternative hypothesis in this context of comparing different groups, we can represent this graphically as well. So this is our alternative hypothesis, and very approximately the alpha and beta align in this manner. So if we have a smaller alpha, our power will be smaller. Power and alpha are inversely related on a logarithmic scale, so that we want to optimize this balance between power and alpha. If the means here are more different, so if this distribution shifted to the right, that would mean we have more power. But we can see here that may not be actual biological reality. We may have a certain difference between the different groups, and that will affect our power to distinguish between these different groups. So we have this trade-off. If alpha is smaller, then power is smaller. If alpha is bigger, we have more false positives, but then our power is bigger. And that's why measuring the PPV for a range of alpha and power values, or pairs of them in effect, can be a way of determining our optimal value. So we just want the maximum PPV possible for our parameters. And what we can think about is that we can measure this effect size, what we're interested in is the biological effect, and Cohen's d, which is several different formulations, but roughly speaking, it's a bit like our pooled t-test value, that we have the difference between the means of our two different samples divided by the pool standard deviation. That's in effect what we're looking at. So we can think of this as being approximated by the difference between the means here. That was 10 in the last example, and this was 12. As a function of the pool standard deviations across the different groups, where obviously they have similar standard deviations and similar sample sizes. So if we think about the relationship, if we chose an alpha value of 0.05, it might be anticipated in experiments to possibly use a power of at least 90%, which means beta is 0.1. So you can think about that graphically, how those two distributions are layered on top of each other. As I try to draw graphically with a slow pen, that if we choose some alpha value here in the middle of the distributions, then we have this area here that corresponds to areas that are beyond our alpha value threshold. And then on this side here, on the other side, those are the ones that are false negatives. And these ones here in this area here that are two positives. In the same way, on the left-hand side here, we have ones that are two negatives that fault match our null hypothesis. And here, beyond the alpha value, those are our false positives. So you can think about this as the area under the curves. We're trying to balance this issue. So this very much depends on the design of the experiment. So what's worth noting is that this correlation is not linear. So we can see how if we change our alpha value from being about 0.05 here, so alpha is down here at the start here, we get a corresponding power of about 0.64. But if we relax alpha to be 0.12, we'll get more false positives, but the power will increase to 0.8. So we'll get more true positives. And the question is, what's the ratio? So you can see here, based on the alpha values, that it's not a linear relationship, and that's why we need to use something like PVV as a way of discriminating what's the kind of optimal balance for these. And it's not necessarily the best choice just to leave alpha at 0.05. That may not give you the best outcome. So what matters then, obviously, here is how different are different distributions. So you may have some difference between them. In this case here, you can see there's quite a big difference. So therefore, we're trying to use use some sort of alpha value threshold here. We might be able to look at the area in the curve that are false positives in this block here are going to be quite small. Then we have our ones that are false negatives here in this area here that are comparatively larger. These are true positives over here, which is a large area size. And these are our true negatives over here. So this example, we've got d equals 0.8 between these different groups. And that's kind of how we can map these kind of our conceptions of true positives, true negatives, false positives, false negatives onto these kind of differences. And sometimes you might see different names for the things like the CV, the critical value, and that refers to the point in the distribution where we're differentiating between those data aligning the null hypothesis versus the alternative hypothesis, if you want to fit into that kind of hypothesis-driven approach. So in practice, what we can look at here is different situations where we have alpha is equal to 0.05 and that power is 0.64 like our previous example. And that could mean if our null is at 10 and alternative is at 12, that can mean if our threshold value is 11.64, remember that comes from looking at the alpha value, kind of in this, assuming this is a normal distribution, we can get the z-score corresponding to that value. We can then map from the null distribution to our alternative distribution to calculate that area under the curve corresponding to the power. If we shift alpha to 0.12, what we're actually doing is we're shifting this threshold left and we're decreasing the value. So you can see that shifts left. That means we have a larger pink area. So the pink area, remember, that's the false positives, and these are the true negatives in green. And these are the true positives has now increased. And likewise, the false negatives, the ones we missed, the type 2 error, has decreased. And therefore, we've determined what's the optimal balance between the different ones, and drawing your distribution can sometimes be useful in trying to understand that. So how do you get more power? This is always a challenge. Ideally, we want distributions that are more distinct, bigger difference in means, but also smaller standard deviations. More samples means we have better accuracy in determining the actual true effect sizes. Another thing we should do in terms of thinking about what we're looking at if we're doing many tests is also to plot the p-values. So think about it like this, that down here on this lower half here or beyond the dotted line, we could have this area region here. So that's here. That conforms to our uniform distribution, which we'd expect for our p-values if we have no effect. So if we have no effect and we choose some alpha level of 0.15, that means we get, and we do 100 tests, we'll get 15 that are false positives, and that corresponds to this yellow area here. Equally, we also have the other ones, the 85 that are true negatives. That's the ones here. If we consider then that we have some fraction of tests that are actually ones where we have an effect, you can see here we have our true positives here, and this depends on our power, which is not explicitly stated here, but let's say we have 20 tests applied here, and let's say our power is 0.75. That means this green area, which is our true positives, corresponds to 15, and our false negatives corresponds to 5. And that means we can calculate our PVV. which is going to be 15 over 15 plus 15. So it's just 0.5 here. So this is not a great distribution, because if we want to examine these samples or features or whatever more carefully, it's 50-50 as to whether they actually have the true effect. And this repeated testing problem is something that we see when we think about the links between different foodstuffs and your relative risk of having cancer. So everything has been associated with cancer at some point, depending on the shape or form. And this repeated practice of taking small sample sizes and assuming that the point estimate of the association is robust and not considering the uncertainty associated with the feature can mean that you can get these spurious associations that are kind of meaningless. And you can kind of see when you aggregate them all together that most of them kind of are very close to a relative risk of about 1. And this is illustrated further in David Culkin's paper from 2014, that if you take a bunch of simulated tests where you can compare 2 different groups where the data is just entirely random, you expect a distribution like this. So this is the distribution of the differences. So you can see it's bell-shaped, and in practice there's no difference here. But you see that some comparisons inevitably will have extreme values, just spuriously. So we simulate 100,000 t-tests in this manner, so we expect a uniform distribution like this. But you can see there that inevitably some tests will have small p-values just by chance. And that's what I say when you have data. Watch your p-values. If you have a gene expression experiment where maybe the effects are sudden, you expect a uniform p-value distribution like this. If you don't have a uniform p-value distribution, or something that's approximating that, you need to think about what model are you using. Is the model appropriate? Does it make sense? Because if you don't have a good model, you'll get lots and lots of genes or whatever with the small p-values, but they're not biologically meaningful. So if you're very, very careful about the tools that you're using, and that's very, very common in tests that you see published all the time, that they give very, very spurious results. If we look at this further, where we have this distribution here of the effect, the repeated testing of a bunch of different tests will always give you this shape where there's some sort of mean, but also ones that are at extremes. So either we detect effects that are not present, or miss effects that are actually different. This is where we have a true difference. You can see here that we have far more small p-values, but also that we have many tests where we have these false negatives. So they might be ones where we miss. You can see are shown here. And these are all ones with true. So there's no false positives or true negatives in this example. So you can see that even if we have true effects, if we have we only have a certain power to detect these true effects. And that corresponds to 78% if we have 16 per group in this instance. If we look at other instances where we have 4 per group, we'll find that only 22% of 0.05. So if we decrease the sample size, our capacity to detect true effects is now much, much smaller. So our power has decreased, and we have far more false negatives that have no detectable effect, a detected effect. So you miss many of them. So having more samples is fundamental to what we do, and in many cases that can mean that we actually don't do an experiment because we have insufficient samples, and it's actually pointless to do because we have insufficient power. So this obsession with p-values is very much a phenomenon that's developed over a series of decades, and it's not based on any logical reason. Ronald Fisher introduced this idea about p-values in 1920, but it was just an evaluation of randomness and observation that this is a percentile on distribution. And then there's other processes based on Pearson and others who look at this approach, you're looking at true positives, false positives, and so on, but don't focus on p-values. So this issue is that p-values are misused in the context of having false positives and false negatives, and thinking about how can we adjust for these confounding effects that we may not have measured in our model. So that's why I think it's very, very important to think about, if you're coming at things from a biological perspective, is to think about the biological context of what you're talking about. And if you're going to talk about significance, think about significance in the context of the biological work, that a small p-value does not necessarily mean anything. So for a lot of biological experiments, this idea about statistical significance is simply a mirage, and it can be associated with simply a bad hypothesis, bad experimental design, insufficient samples, and poor use of models. One way of thinking about this and our p-values and the capacity with the model and the null hypothesis is about S-scores. So S-scores are refer to S-values, refer to coin tossing equivalents of p-values. So it's kind of this distribution here kind of gives us the sense of our p-value and the number of coin tosses we would require to get that sort of situation. So think of an S value as kind of like a surprisal or maybe a Shannon value. So if we get a p-value of 0.26, this corresponds to 5 coin tosses in a row. So 5 coin tosses where we get heads in a row. If we get a p-value of 0.004, that's the equivalent of 8 coin tosses. But if you keep tossing a coin, it is inevitable that you will eventually get 5 or 8 or whatever number it is of heads in a row if you just keep tossing those coins. And that's the issue across the scientific community, that so many people are doing similar experiments. The ones that are reported are ones that just happen to have many, many heads out of a bunch of coin tosses. And whether that's robust in other samples is also something that is important to examine. So we can think of this visually then about our effective power on the sample size. So if we have two alternative hypotheses like this, where the variances are very, very large relative to the difference here, even though the effect size is big, the PPV may not be very, very high. So here the power is just 0.26. So that means many of our tests will not actually, many of our capacity to detect true effects is very, very poor. If we increase our sample size, we'll see that we actually get a better power associated with our effects. And if we continue that further, our power will tend to increase. And in fact, that affects our PVV. So roughly speaking, if you increase your sample size, it's a function of 1 over n is how its affects this kind of spread of our values that we have. So that's why if you go from increase your sample size from say 1 to 10 to 100, we'll see a corresponding increase in our PPV and our accuracy of our overall experiment. So if n equals 10, our probability to detect a 10% increase in the expression of something with alpha set to 0.05 is 84%. That's what we're saying here. So we also have to think about this. Is 10% biologically meaningful? That's our minimum threshold for what's actually useful in our context. Is 1% actually of interest? Probably not. And do we actually have a power to detect that in the context of our experiment? Is a 50% increase interesting? Probably. And what's the probability of us detecting that? Another way of looking at that, for the same values, as we go through different alpha values from ones that are smaller to larger, is that as we increase the sample sizes, our power will increase. So if we set an alpha value to be at 0.05, you can see here for small sample sizes, our power will be low, but it'll increase as we go higher, say from 3 to 7. In the same way, if we have more stringent alpha, our power will still increase, but note that it's still very small. If we have n equals, say, 6.5, our power would just be 50% for an alpha value of 0.005. And this is all with the very large effect size of d equals 1, which is large in any context. So if we take bigger effect sizes, then on the other side, and increase d from d equals 1 to 1.5 to 2, we'll see that our power increases in the same way. So if you have a true biological effect, our power will be very high to detect that if it's very, very extreme. However, in most experiments, you're not even going to get d equals 1. You might get d equals 0.5 if you're lucky. In a practice, most of what you'll find is you get d equals 0.2. So your power to detect those two effects, if you have small sample sizes, n equals 3 in this instance, is going to be very, very small. So if you have n equals 30, your capacity to detect two effects will be much, much higher. In the same way, you can plot power versus d. So you can see there for if we have small effect sizes of 0.5 or 0.2, our power to detect these for these range of values with n equals 3 is very, very small. So obviously, if n is higher, we'll get values that are up here, distributions following this line, and that'll be better. And that's why having n equals 3 really is going to mean we're actually going to miss many things. So that's the end of this portion of this video. Please see the next video on how we can get around this using multiple test correction.